It's 4 o'clock, right, on the Rolex watches here. I know you all know why we are here today. I mean, because you have read the press release and also the mail that was sent by the Director General this morning. So I would like maybe first to recall the aim of this seminar. I mean, our colleagues from Opera have made an intriguing measurement. And after, I'm sure, a lot of and harsh work they have done during many months and in order to try to pin it down or understand it, they have decided to make it public. And I think the aim of this seminar is really to share this with you, to show you what they have done, and of course to trigger questions from your side and later from the community. I think this is the aim of this seminar. So the seminar will be given by Dario Otiero, who is from Institut Physique Nucléaire de Lyon, and he's currently the physics coordinator of the Opera collaboration. So I let him now show you the presentation.
Okay. Thank you very much. Good afternoon, everybody. So the spirit of this seminar was well summarized by Philippe, and I just want to add that we are very happy to be at CERN today. We thank CERN for the possibility that was given to us to give this seminar, and also for the continuous support in the operation of the CNGS beam. So as you probably know, today I'm talking on behalf of the Opera collaboration. This is a collaboration including 160 physicists from 30 institutions and 11 countries, mainly from Japan and Europe. And for this special result, we also profited from the collaboration of individuals and institutes which worked with us for various issues related to the metrology measurements. So I just quickly report here many contributions from CERN, from the CNGS group, the survey group, the timing group at CERN, and the PS group. And then we got also a very important contribution from the geodesy group, from the Università La Sapienza in Rome, the Swiss Metrology Institute METAS, and the German Metrology Institute PTB. So the principle of the measurement that we are going to discuss today is quite simple. It's a classical measurement. So it's a ratio among a precisely measured baseline and time of flight. So in order to measure the time of flight of neutrinos, we need to tag the neutrino production time, and we need to tag the neutrino interaction time by a far detector, which is Opera. The other ingredient is the accurate determination of the baseline, which comes from geodesy. And since the effects that we are going to see are smalls, we need a long baseline in order to match the accuracy of the timing measurements. And in our case, this baseline is 730 kilometers. And then the other aspect of this measurement is that this was a blind analysis. So we opened the box after we reached an adequate level of understanding of the systematics. So I will just quickly go through the past experimental results. We had a result from an experiment at Fermilab in 1979, where they were performing this measurement on high energy neutrinos with energies greater than 30 GeV. They tested deviations with respect to the speed of light, comparing the muon neutrinos and the muon velocities. And the result was that these kind of deviations were less than 4 times 10 to the minus 5. Then, as you all know, we have the results related to the observation of the supernova 1987A. In that case, electron antineutrinos were observed, mainly from the inverse beta decay, in the 10 MeV range on a baseline of 168,000 light years, which is very long. And this is a negative result, which tells you that there are no deviations within for less than 2 times 10 to the minus 9. And then we had the MINOS result in 2007. This is with mu neutrinos over 730 kilometers with the energy of neutrinos peaking at 3 GeV and the tail extending above 100 GeV. And in that case, the result was positive. It was 5.1 times 10 to the minus 5, although not significant because it was just 1.8 sigmas. The OPERA experiment was designed for another purpose in order to study the mu neutrino to tau neutrino oscillations. So it's a detector with high space accuracy in order to detect the tau decay topology. In order to perform this study, the main subdetector is the so-called ECC brick, which is a sandwich of lead plates, which are 1 millimeter thick, and photographic films, nuclear emulsions. And this allows to detect with micrometric accuracy the features of the tau decay. The bricks are passive objects, so they need electronic detector in order to find where the neutrino interaction occurred in the target, and also reconstruct the muons, which are typically particles crossing many walls of bricks in our detector, and also attribute a time to the neutrino interaction. So there are, in this figure, you see these so-called electronic trackers that we will discuss also for the neutrino velocity measurement. Here you can see a picture of the OPERA detector in Gran Sasso. So you can see the walls where the bricks are arranged. So the detector is made of 2 supermodules. Each supermodule includes 31 walls. We didn't fill completely the detector. You see that there are some empty spaces. And you can see the bricks in this wall structure. And then you don't see in details, but there are scintillator planes in between each pair of walls. And then there is a magnetic spectrometer in order to measure the momentum of the muon and their charge. So the target tracker is the detector which is in between each pair of brick walls, and it's a scintillator plane. It's a scintillator biplane with the 2 views, X and Y, and is made of module of scintillator strips. Here you can see one module during the construction. So one module includes 64 strips for a total width of 1.7 meters and a length of 6.9 meters. The strips are read out with wavelength shifting fibers on the 2 sides, and these 64 wavelength shifting fibers are then read out with a multi-anode photomultiplier. So there is, you can imagine that for each super photomultiplier there is a front-end board which is associated to it on the 2 sides of the module. In fact, the detector, the EQ system works in a triggerless mode asynchronously by putting together these front-end boards, which are about 1,200. They are distributed all around the detector, and in particular there are 1,000 of these front-end boards for the readout of the scintillator planes, and the data are then output on a gigabit Ethernet network. So since the detector works asynchronously, a very important ingredient is the synchronization of all these front-end boards, which is provided by a clock distribution system which works with 10 nanosecond granularity, which delivers the UTC time to all the front-end boards, so that then the hits which are acquired by each front-end board can be aligned in time, and the event can be reconstructed. And all this system is handled by this OPERA master clock, which receives a signal from an external GPS. It receives a synchronization system once every millisecond. And this OPERA master clock card has a very stable oscillator, which has the stability comparable to a rubidium clock, so that among 2 synchronization, the time is kept with very high accuracy. All these front-end boards, they are read out with the same concept, which is the so-called mezzanine DAQ card, which includes a CPU with embedded Linux, a memory, an FPGA, which, for instance, performs the tagging of the event, the clock receiver, and the circuit which puts the data on Ethernet. So here you can see a few examples of events detected by the electronic detectors of Opera. Here you have a new mu charge current interaction candidate, where you see here the point of interaction, the hadronic shower, and then the muon which is crossing the two supermodules. This is a neutral current event where you just see the hadronic shower. And these are muons which are coming from neutrino interaction occurring in the rock in front of the detector, which will also be used for this measurement. So the CNGS beam is going from CERN to the Gran Sasso underground laboratory over this baseline of 730 kilometers. You can imagine that the full width, half maximum of the beam in Gran Sasso is about 2 kilometers. And in the picture you can see also a sketch of the Gran Sasso laboratory, and on top of the laboratory you have an equivalent thickness of about 1,400 meters of rock, which strongly reduced the rate of cosmic rays. We have underground a rate of 1 muon per square meter per hour. So there is about a factor of 1,000 reduction with respect to what you have on surface. And now I will say a few words about the CNGS neutrino beam. So protons are accelerated up to 400 GeV by the SPS. And this is done on a cycle which lasts 6 seconds. And then the entire content of the SPS is extracted in 2 extractions, which roughly correspond each one to 5/11 of the circumference of the SPS. And they last 10.5 microseconds. So the extraction is performed by a kicker magnet. The 2 extractions are separated by 50 milliseconds. And the nominal beam intensity is 2.4 times 10 to the 13 protons per extraction. So this is a pure mu neutrino beam with an average energy of the neutrinos of 17 GeV, which is then sent to Gran Sasso traveling through the Earth crust. So here you can see the sketch of the beam. You have the proton line up to the target, then you have the system of the horn and the reflector in order to focalize the positive mesons, which are then sent in this decay tube, which is 1 kilometer long. And then there is an hadron stop and 2 muon detectors at the end in order to measure the profile of the muons which come from the pion decay as the neutrinos. So now we come to how we select the events related to the CNGS beam. So this is done like in other experiments, like in MINOS or T2K, by using the GPS system. And this allows to synchronize the 2 sites in order to compare the time of production of extraction of the protons from the accelerator and CERN and the time of detection of neutrinos in Gran Sasso. So with the standard GPS systems, you have a typical accuracy of 100 nanoseconds. And since the beginning of the data taking in Opera, we were opening a window of 40 microseconds, plus minus 20 microseconds, where we were comparing the time of the events in Opera with respect to the time of the extraction of the protons from the SPS, the so-called T-kicker, plus the time of flight computed by assuming the speed of light. So this is a very broad window, as you see. And it was completely matching the accuracy of the standard GPS systems existing at CERN and in Gran Sasso for this kind of coincidences. So here you can see a picture that we published in 2008, I believe, in one of the first papers, or 2007, one of the first papers of Opera, where we can see the time distribution of the events recorded by opera. So this is on a very large window, plus minus 50 milliseconds, and you can see that there is a flat distribution due to the cosmic rays, but then you see the two neutrino spills, which are separated by 50 milliseconds. And if you zoom on the two spills, you can see a very clean distributions of the events which are on time with the beam, practically without background. In fact, you can measure the background by looking, for instance, in this region, and it is of the order of 10 to the minus 4. So this selection procedure, by opening this window of plus minus 20 microseconds, we have been keeping unchanged since 2006, is just a procedure in order to find events which are on time with the beam. So this is another picture of a distribution produced in 2008. If you apply this principle as I described before, you can see that you find two very clean distribution with practically without background around. But you see also that these distributions of the neutrinos, they are not flat at all. They are different if you compare the first and the second extraction. And this is due to a different real timing of the protons with respect to this kicker pulse trigger. So if you would just attempt to measure the neutrino velocity by taking the average of these two distributions and without accounting for the features of the beam, you would find different values for the first and the second extraction. So in 2006, when we started this work in order to find the events in coincidence with the CNGS, we realized also that we could do better. And in order to do better, one has to take into account these two factors, that the distribution of neutrinos is not flat because the protons are not flat, and also this different timing. So the need is to measure precisely the proton spills. The other thing that we realized is on the side of the GPS. So as I said, we were using standard commercial GPS for well, high accuracy applications, but not comparable to what you will see in a few minutes. So this is a picture where the two GPS which were installed in Gran Sasso at the time, and they are still there, are compared to a cesium clock. So this is the phase of these two GPS clocks with respect to the cesium. So you can see similar features. You can see that there are some large oscillations of about 60 nanoseconds. You can also see that there are big differences, so don't look at the absolute value of this scale, but you can see that there are about 150 nanoseconds difference on average between the two clocks because they were not precisely calibrated. So the other need, in order to go to a more precise evaluation of the neutrino velocity, was to have something which provides an accurate time synchronization of the beam. So we have been profiting of a very good collaboration with the CERN timing team since 2003. This has been really fruitful and brought to this measurement where we joined the techniques used commonly in high energy physics and metrology techniques. And this was a major contribution from our collaborators from CERN. So together we decided in 2008 to go through a major upgrade of the timing system. And this upgrade allowed to perform the measurement that I will describe in a few minutes. So the good points of opera for this neutrino velocity measurement are the following. This is a high energy neutrino beam, which means high statistics. And as you will see, the measurement is based on about 16,000 events. So this gives a very good statistical accuracy. And then the other ingredient is this sophisticated timing system, which we decided to install in 2008. And this allows to reach a synchronization level around 1 nanosecond between the two clocks which are at CERN and in Gran Sasso. And then there were many calibration works on the timing chains at CERN and in Opera in order to bring the knowledge, the systematic knowledge of every element at the nanosecond level. The other ingredient, as you have seen, are the protons. We need precise measurement of the neutrino time distribution through the proton distributions. So we installed a device at CERN in order to perform these measurements on the protons. And then the final ingredient is the knowledge of the baseline. So as you will see, with a dedicated geodesy campaign, we managed to reach 20 centimeter accuracy over 730 kilometers. So the result of all these ingredients at the end is to achieve a 10 nanosecond overall accuracy on the time of flight of neutrinos with comparable statistical and systematic errors. Now in this slide you see a sketch of the new system which was installed in 2008. So we didn't want to discard what was already existing, operating at CERN and in Gran Sasso. So at CERN there was one of these conventional receivers from Symmetricon, which is called XLI, which is the timing source of the general machine timing chain at CERN, which then feeds all the timing of the accelerators. In parallel, in Gran Sasso there was this receiver from ESAT, which was working since the 90s. It was already used by the macro experiment, and this was sending the time underground. So we decided to install a twin system, which is, there are two setups completely equal in Gran Sasso and at CERN, which include a special receiver for time transfer applications, which is called Polar X, which is coupled to a cesium clock. And then there is a DAQ system which continuously compares the time, every second compares the time of this special receiver with the time of the standard receiver. And this allows us to compute the corrections. And the same thing is done at CERN. So this allowed us to improve the systematic accuracy to reach a synchronization at the nanosecond level, but without touching what was already existing both at CERN and in Gran Sasso. So this slide is rather technical. I will go quickly through that. One point that I would like to stress is that these kind of techniques that we have been using are maybe unusual for high energy physics, but they are quite common in metrology for time transfer application between the many metrology institutes which are operating in Europe. So this Polar X receiver was characterized by the Royal Belgian Observatory, and it was already used in time transfer measurements. So the frequencies, the reference frequency is provided by a cesium clock, and then the receiver is capable of performing an internal time tagging of the 1 PPS, which is synchronous to the cesium clock with respect to the individual satellite observations. And you get the data offline, which allow you to perform all the corrections which are needed. And these data are written in this format, which is called the CGG-TS. And the other point is to use this code, which is called the P3, which is based on the measurement of two different frequencies in order to get rid of the corrections due to the different speed of light in the ionosphere with respect to the speed of light in vacuum. So I said that this is this is a standard technique in metrology and established a permanent link at the 1 nanosecond level between the reference points at CERN and in the Opera timing chain. So here you can see a picture of the two systems. So this is the installation. This is the installation operating at CERN in the CCR in Prevestin. And this is the installation operating in Gran Sasso. So you see the high accuracy system side by side to the standard one, which was operating in Gran Sasso. There were 3 clocks. We were working with this one. And we have been working for all the data taking with the same clock. So a few words about the GPS. You know that the GPS allows to find your position on the Earth. Well, it's more general than that because it resolves your 4 vector In fact, it determines at the same moment X, Y, Z, and your time. X, Y, and Z, they are described with respect to a geocentric system, with a Cartesian system with the origin at the center of the Earth. And you can find your unknown by performing 4 satellite observations. So this is a system of 4 equations in 4 unknowns, which allow to determine at the same time the position and the time. So this is the standard GPS operation. Then there is a special operation which has been used for this measurement, which is the so-called common view mode. So there we know already the position, because the position we can measure from time to time with the GPS data and assume that it's stable. You will see later how it is stable. And then by knowing the position, you can just find out your time. And if you do it on 2 places, 2 distant places of the Earth by looking at the same satellite, you get some, you benefit that some systematics of the transmission of the radio waves in the ionosphere will cancel out. And the reason is that the distance of the satellite from the Earth's surface is 20,000 kilometers, which is quite large with respect to the distance among the 2 sites, which is 730 kilometers. So by doing this common view mode, which is something that you have to perform, it's an offline analysis that you have to perform, you can accurately synchronize these 2 places at 1 nanosecond level. This is yet a kind of standard technique in metrology. Okay, this is what you see when you perform this kind of offline analysis. So these are the corrections with respect to the standard GPS that you have seen at this kind of oscillation. So at the end, the corrections correspond to the blue points. The red points are before quality cuts on the quality of the signal from the satellites. Also, this is a standard procedure in the analysis of this data. And then you get these kind of corrections. Every point is computed for a neutrino interaction in opera. So you see that there is an offset between the standard GPS clocks at CERN and Gran Sasso, the pre-existing one of about in between 200 and 300 nanoseconds, and then you see the oscillation of the standard clocks, which are corrected by this high accuracy device. Okay, so by itself, these 2 systems were calibrated by the Swiss Institute of Metrology, METAS, and their specification, they were corresponding to this 1 nanosecond level synchronization. We could have believed that, but when we knew that there was this result, we decided to go through a completely independent confirmation by another metrology institute, which is called PTB in Germany. So they took data with a portable device, which was already used for this kind of operation in order to synchronize the US Naval Observatory, which handles the GPS, to this PTB institute in Germany. So they took data for 2 weeks at CERN and in Gran Sasso, and they found an offset of 2.3 nanoseconds with an error of 0.9, which is completely compatible with the calibration accuracy of the 2 GPS detectors, Polar X GPS detectors from METAS. Now we come to the timing of the protons. So in order to measure the timing of the protons, we used a fast beam current transformer detector, which is installed on the CNGS beam line. This is a device with large bandwidth of about 400 megahertz. And it's coupled to a waveform digitizer, which works at 1 gigasample per second. And the acquisition window of this waveform digitizer is triggered by a replica of the kicker signal. So we use the kicker signal just as a kind of pre-trigger to open a window in order to find events in Gran Sasso and to start the digitization of the protons. We do not use it for accurate timing. So these waveforms, which are acquired by the digitizer, they are UTC stamped and stored in the CNGS database for each spill. So this is a quite large amount of data, but we have really the proton waveforms for each, for all the spills which have been extracted to the CNGS target. So here you can see a picture of the device. It's this small one, it's not the large one, during a calibration which was performed in 2010 by injecting the signal from the cesium clock in the test input of the BCT. So the shape of the protons, as you have seen, is not flat. It depends on the way the beam is produced by the PS and injected in the SPS. And this is done, half of the SPS, roughly half of the SPS, is filled with 5 turns of the PS. So the beam which is contained in the PS is shaped with an electrostatic septum. So these are the 5 parts of the beams in the phase space, which are then injected in the SPS. And this operation implies quite some large losses, which are actually limiting the performance of the CNGS. We cannot go beyond a certain limit, which is due to radio protection requirements at the level of the PS. So these losses, then they create the structures that you see here, which are related to the 5 turns. And as I was saying before, all this relies on the fact that the SPS circumference is 11 times the PS circumference. So you can fill it with 2 injections from the PS, and each one includes these 5 turns. So this is an example of the waveforms which are measured by the BCT. So you see that there is this oscillation here, which if you zoom, it corresponds to the radio frequency in the SPS at 200 megahertz. So you see the separation of 5 nanoseconds corresponding to the SPS radio frequency. So when you have, as I mentioned, all the waveforms are stored in the database. So for each event that we record in Opera, we are able to associate it to its proton waveform. Of course, you have seen we don't know within the spill which is the proton which has produced the neutrino which interacts in Gran Sasso. So we can perform this measurement of the neutrino velocity in statistical way by comparing the distribution of neutrinos in Gran Sasso to the waveforms which are recorded at CERN. So in order to do that, we sum all the waveforms corresponding to the events which are recorded by Opera. And this has to be done separately for the 2 extractions because, as I mentioned, they have a different timing. And then we can compare this kind of distributions to the neutrino events recorded by Opera. Timing. So the answer is yes, because well, first of all, there is a slight difference between the proton velocity and the C in bringing the protons to the target. This accounts for a few picoseconds. And then also the particles, the mesons which are produced by the interactions of the protons in the target are relativistic. So you can get an idea from this analytic formula, and you have a difference with respect to the, if you assume that everything, the mesons and the protons, they travel at the speed of light, or you take into account all the details of the velocities of the mesons, you have a difference which goes as the gamma square of the mesons. And this can be precisely computed because we have a full simulation of the beam line, and it's a completely negligible effect. And it goes also in the direction of delaying the neutrinos. Okay, so in this slide there is a sketch of the principle of the measurement. So we measure the proton waveforms with the BCT. Then we know precisely the distance from the point where they are measured, the BCT and the opera reference frame, with the geodesy and also the knowledge of the beamline at CERN. We can shift the waveforms measured at CERN. These waveforms are tagged with respect to the UTC. We can shift them by taking into account the time of flight, which corresponds to this distance divided by c. And then we compare this shifted waveform to the data recorded in Gran Sasso, which are also UTC time tagged with this high accuracy system, which synchronizes at 1 nanosecond level. Then by computing the difference between the two distributions, we can estimate a possible deviation of the neutrino time of flight with respect to this time of flight computed by assuming c. So the geodesy, it's a very important ingredient, and in order to be accurate, we had a dedicated campaign at Gran Sasso in 2010. So the main difficulty is not to measure the positions outside, but to bring them underground, as you can expect. So during this campaign, there were two new GPS reference points which were installed at the two ends of the tunnel, of the highway tunnel. And then this information was brought underground independently from the two sides with a set of optical triangulations. And by doing this, we introduce a systematic inaccuracy, an error which is of the order of 20 centimeters, which is dominating our measurement. So I have also to say that when these two independent measurements, they matched at the center, they were in very good agreement. So here you can see then the coordinates of these external references in the GPS reference system. They are expressed in this ETRF 2000, which is a European global system, which accounts also for effects related to the Earth dynamics, the continental drift. And by using these measurements, you can combine to the measurements taken at CERN in order to compute the baseline. So the measurements which were taken at CERN were taken when the CNGS beam was started in 1998. All these geodynamics calculations are quite accurate, so we could have trusted the porting of this measurement through time. But then as a cross-check, we decided to repeat again the measurements at CERN and in Gran Sasso simultaneously. This was done in June 2011 in order to get more confidence on the result, and this confirmed the other result. So this is the distance between the BCT and the origin of the opera reference frame, and it is known at 20 centimeter level, which are dominated by this procedure to port underground the external measurements. By having this high accuracy system, we can also monitor the position of the antenna in the external laboratory. And this is what we see on a very long period. So you see this smooth curve which corresponds to the continental drift. And then in April 2009, there was the effect of the earthquake, which displaced the laboratory by about 7 centimeters in the east and north direction. So this is just to give you an idea of the accuracy with which you can perform this kind of measurements, which is maybe unusual for high energy physics, but is standard for high accuracy geodesy measurements. Okay, then we have the system is not so simple because we have two chains for timing at CERN and in Gran Sasso. They must be calibrated piece by piece, and we use two techniques which are as inclusive as possible. So the idea is to measure each time the delay between two reference points in the timing chain without, for instance, measuring single elements with different technique, like, for instance, optical fibers. We do not measure the optical fiber with other techniques, but we try to perform an inclusive measurement which is directly related to the timing used by our measurement. So there are two techniques in order to do that. The first one is the portable cesium clock. So you have one of these cesium clocks, and you can measure the phase of its signal, which is produced once per second, with respect to the signal at the start of the chain and at the end of the chain. So there are various ways of doing that, either with a digital scope or by performing a time tagging. And then the other technique is to perform a double path measurement. In this case, you introduce another path of propagation of the signal with an optical fiber parallel to the path that you have to measure. And at the end, you measure the difference between the two times, the two travel times of the signals. Then, by using exactly the same chain, by just reverting the transmitter and the receiver, you chain the signal from the end down to the start, and you measure the sum of the two paths. And then by solving a system of two equations in two unknowns, you can measure separately the additional path and the unknown path. And we have been using these two techniques in parallel for all the measurements we performed, and they gave the same result without the systematic uncertainty, which is typically at the nanosecond level. Okay. For what concerns the BCT calibration, this is a more delicate story. We performed a dedicated beam experiment. So this delay is mainly the cable which is used to bring the signal from the BCT to the waveform digitizer, which is in the former UA2 counting room. But we, as you have seen, we tried the first attempt by using the cesium clock, the portable cesium clock, and injecting the signal in the BCT. But then there was the question, is this really representative of what the protons do? And then we decided to check directly what the protons do in the BCT, and this was done with this dedicated beam experiment where we had two beam pickup detectors on the line. So we tagged the time, the transit time of the protons in these two detectors, and by knowing with the survey, the geometry of the line, we could predict the transit time of the protons in the BCT, and then compare to the signal that we were measuring in the counting room. So this kind of technique gives an accuracy of 5 nanoseconds. And as I said, this delay is mainly determined by the cable, but we wanted really to be sure to have something which was representative of what the protons do. So in order to do that, we used a special beam condition. We used the LHC beam, which has bunches of 1 nanosecond, and they are separated by 50 nanoseconds. So you get a comb of this kind of point-like pulses that then you can overlay. This is before the calibration. You can overlay with the signal of the BCT, and this is the result after having overlaid the two, which allows you to measure this delay of 580 nanoseconds. So here is a description of the timing chain at CERN. So as I said, we have this standard GPS, pre-existing GPS. Then we have the high accuracy one, the Polar X. And we have this DAQ system, which is made by these devices, which are commonly used at CERN for time tagging, which are called the CTRI. And there is one of these devices in the private central control room, where we have defined this reference point, which we call the T-CERN, which will be then compared to a similar reference points in Gran Sasso for this synchronization at the nanosecond level. Then this timing is distributed through a system to the different CTRI, and we measure this delay by using the cesium clock and also by performing a two-way measurement. It goes in the CTRI, which is sitting in the UA2 control room, where it is used to time tag the kicker signal and also to start the waveform digitizer window, which is started 30 nanoseconds after the time tag of the kicker signal. So then the BCT is connected through this cable to the waveform digitizer, and there is this additional delay with respect to the transit time of the protons in the BCT. The BCT is about 700 meters far from the target. So in Gran Sasso we have a similar picture where we had the existing GPS system, then the high accuracy one which makes the link to CERN. This is the reference point for the time link between CERN and Gran Sasso. And then the signal of the standard GPS signal, the system in Gran Sasso is sent every millisecond underground to the Opera master clock, which is here. This delay was measured also with two techniques by using the portable cesium clock and this two-path measurement. And then the Opera master clock distributes the signal to the sensors, and we take as a reference the last sensor of the chain. The sensors in each chain are aligned by dedicated measurements. And also this delay was measured in two ways, both by using the cesium and the two-way technique. And then we had to also to measure the latency of the FPGA in performing the time tag. And this was measured by performing a time measurement at the same time with the data acquisition and with an external digital scope. And then you have the delays related to the detector. So I will go in more details later, but you can imagine that you have a delay from the time you get an interaction you get a particle which is measured, which produces light in the scintillator strip, and the time the FPGA sees a trigger. So you have the transit time in the photomultiplier, the time response of the analog chip which produces the trigger, and so on. So these delays are on average, the total delay of the detector response is on average about 60 nanoseconds. So this delay of the detector was measured also by using a technique with a picosecond laser, UV laser, which was injecting the scintillator strips in different points. And then we could extrapolate the time response down to the surface of the photocathode in order to get the constant time which is given by the transit time in the photomultiplier, the response of the analog chip which produces the trigger, and the porting of the signal to the FPGA. So then there are other effects like the position of the event in the strip, the dependence on the pulse height of the trigger delay on the pulse height, and the quantization effect, which are accounted by simulations which take into account parameterizations of the time response of the strips which have been derived from laboratory measurements. Okay, so this is a table. I don't want you to go through the numbers, but which includes all the delays which concern these measurements. And what is interesting is to see that everything has been measured with different techniques. So all the delays of the chains were, as I said, were measured with this portable cesium and also the two-ways measurement. So this two-ways measurement, for instance, for what concerns the distribution of the UTC time at CERN, we kept permanently working since July 2011 up to now. So this is a plot which shows you the variations of this delay with respect to the nominal value. And you see the kind of accuracy. Here the full scale corresponds to plus minus 0.4 nanoseconds. So it's well within the systematic accuracy that we have been mentioning before. Okay, now we go to the other side, to the event selection in Opera. So the result of this measurement is based on 10 to the 20 protons on target. As I mentioned, we take both internal and external events, and they have comparable statistics. So the internal events are about 7,500 and the external one 8,500. So the possible bias on external events where the neutrino interacts in the rock, they've been checked with the Monte Carlo simulation, and they correspond to a 2 nanosecond systematic uncertainty when they are added to the internal events. And the way to make sure that there is not a large bias is to require that there is a high energy muon entering in the detector. In this case, the particle is relativistic, and there is no bias on the time of flight. There is little bias on the time of flight of this secondary particle. Then this kind of bias we have been also checking directly, because we could analyze separately the internal and external events, as I will show you in a moment. So once we get the events in the detector, they go through two kinds of corrections. The first one that I described before is the correction of the time link, and the second one is the correction by the position of the earliest hit, which defines the time of the event. So since the baseline was computed with respect to this point, which is the origin of the opera reference frame, one has to take into account the position of the hit, and what matters is the longitudinal position along the beam. And we have an average correction for how the events are distributed of 140 centimeters, which correspond to 4.7 nanoseconds. And this also we have been checking by performing the analysis with and without the correction, and it agrees completely with the Z distribution. Okay, the analysis method. So as I mentioned, for each event in opera, we can get its proton waveform, then we can sum them up, and we can get the probability distribution function, which will represent the time distribution of the events detected by opera. We get two, one for each extraction, because the two extractions have different timing. And then we can enter in this probability distribution function with the time of the event and compute a likelihood function. And we can do this in steps by adding these extra parameters, which describes the deviation from the TOF computed assuming the speed of light. And here you see the result, this log likelihood plot, which gives you the delay for the blind analysis. So you get this value, which is 1048 nanoseconds, which is deliberately large, as I will explain later, in order to prevent that we could infer on the result without really knowing the calibration of all the elements of the chain. So this blind analysis was done by ignoring many facts. So we were referring to a wrong baseline, which was taking as a reference point not the BCT used for the measurement, but by another one, which is in the SPS, because we started like that in 2006. So we just kept this procedure, which is of course wrong and will give you a huge offset. We were ignoring the details of the time response and the DAQ in opera. We were using some old GPS intercalibration, which was done in 2006 by bringing the standard GPS system from CERN to Gran Sasso and looking at the difference between the two systems. We were ignoring the BCT and waveform digitizer delays and also the UTC calibration at CERN. So this results in this very large difference of 1048 nanoseconds. And we decided to open the box to look at the real result in March when we knew all the delays. And in particular, the last one that we had to know was the geodesy. It was the result of the integration of the measurements taken in Gran Sasso with the measurements taken at CERN. So this is the result of the likelihood maximization. So here you have the curves of the protons and the neutrino distribution in opera before performing the likelihood maximization. And then you can overlay them by correcting by the result of the likelihood maximization, which is this 1048.5 nanoseconds. And you see that there is a quite nice agreement. The neutrino events in Gran Sasso are described by the shape of the protons, which is measured at CERN, and in particular you see the leading and falling edges of the distribution, which are quite important in this measurement, which match the data points. This is better shown in this zoom, where you can see after overlaying with the likelihood maximization result, the fronts for the first and second extraction. Now you see that there is a very good agreement between the experimental points and the cube, which is just one of the protons, just shifted by the result, this delta T computed with the likelihood. We performed several cross-checks of the analysis. So this analysis can be performed for the two extractions separately, which have completely different timing, but they give the same result. And then it can be computed year by year. And here you see the data taken in 2009, 2010, and 2011 compared to the overall result. And then we even try to compute this analysis in some arbitrary subsamples, for instance, by taking the data, the neutrino events which occur during the night or the day, and the two bins, they agree within the errors. So we saw a difference of 17 nanoseconds between the two bins, plus with an error of 15. And again, the result is a difference of 11 nanoseconds with an error of 14.3. And then the other legitimate question was to remove the external events. And by taking, this is the result with, which includes external and internal events. By taking only the internal events, you get a result which is compatible within the systematic accuracy that we were expecting from the Monte Carlo simulation. So then, after having performed this cross-check and by knowing all the calibration delays, we could open the box. And this is a table which summarizes the differences between the blind analysis, the situation which was corresponding to 2006, and the final analysis. So as I mentioned, we were assuming a wrong baseline. We were not taking into account the final UTC calibration. We were not taking into account the BCT and the waveform digitizer. We were not taking into account the delays in the detector. And finally, we were not taking into account the time link, but some prior GPS synchronization. So if you take into account all these factors, you get to a global shift of minus 987.8 nanoseconds. And the other table describes, or considering, by neglecting the velocity of the pions, the bias is very small. The bias on the interaction point in Gran Sasso for external events, the measurement of the UTC delay, the measurement of the delay in the distribution of the signal in Gran Sasso from the external clock to the underground all, and the transmission of the synchronization of the DQ system, the FPGA latency, the waveform, fast waveform digitizer trigger delay, the synchronization among the two sides, the systematic uncertainty on the Monte Carlo simulation, which is used in order to evaluate the position dependence, the response of the target tracker, and the BCT calibration. So all these uncertainties added in quadrature, they amount to 7.4 nanoseconds. So this is the as a sampling calorimeter with these LED blocks and the target tracker. And the difference, well, you will see the difference between the two beams, but here there is the result expressed for these internal events for which we know the energy, which is an anticipation of 60.3 nanoseconds, corresponding to an average event energy of 28 GB. So this is not the average neutrino energy in the beam, is for interacting neutrino, is a higher energy. So this is the result by considering these two beams in energy, where we do not see a significant energy dependence within the statistical accuracy of our measurement, which is not very good. When you start taking the internal events, you lose statistics, and you see, then you divide even the sample in two parts, and the statistical uncertainty is large. And here you can see the overall result, for which there is no energy scale, because this includes also the external. The detector at LNGS has allowed the most sensitive terrestrial measurement of the neutrino velocity over a baseline of about 730 kilometers. So we improved by about a factor 10 with respect to the previous measurement of minus. We profited of the large statistics which was accumulated by OPERA, 16,000 events, of this dedicated upgrade of the CNGS and OPERA timing systems, an accurate geodesy campaign, and a series of calibration measurements which were conducted with different and complementary techniques. The analysis of data from 2009, 2010, and 2011, part of 2011, the 2011 run is still going, was carried out to measure the neutrino time of flight for CNGS mu neutrinos traveling through the Earth crust with an average energy of 17 GB. The result of the analysis indicate an early neutrino arrival time with respect to the one computed by assuming the measured baseline divided by the speed of light of 60.7 plus minus 6.9 plus minus 7.4 nanoseconds. So we spent 6 months in various cross-checks. We cannot explain the observed effect in terms of non-systematic uncertainty. Therefore, we present to you today this discrepancy, this anomaly with respect to what we would have expected by assuming the speed of light. And this is has an overall significance of 6 sigmas. So we also investigated the possible energy dependence of the effect in the energy domain which is covered by the CNGS beam, and within the statistical accuracy of the measurement you have seen that the errors are quite large. We do not observe any significant effect. And now I have to add many words of caution from all us. So despite the large significance of this measurement that you have seen and the stability of the analysis, since it has a potentially great impact on physics, this motivates the continuation of our studies in order to identify still unknown systematic effects, and we look also forward to independent measurements from other experiments. And for the same reasons, we do not attempt any theoretical or phenomenological interpretation of the result. Thank you.
Maybe Professor Ting, if you would like, I would like maybe to try to structure maybe a bit the discussion. I mean, so what I propose is that we try first to really address the experimental results which have been presented to us today. I mean, this is the most important. And so since the velocity is a ratio of distance divided by time, and I propose that we first maybe take question about the geodesy, I mean about if there are questions about the distance, then we will take question about the time, and then maybe after we will take question about the analysis. And then finally, what I propose is if at the end some people want to make comment, to ask questions about you know, what they have in their head about theoretical or whatever interpretation or the doubts or whatever. Of course, they are free to do so. We should keep it at the end. And as was really written in the previous slide, I mean, this somehow will be an internal discussion inside the auditorium, because our colleagues who have decided not to give any interpretation of the result. So, okay, so maybe Professor Ting, if you want. By the way, there is this auditorium. Okay, you can use that, but it's very well equipped with microphones. You can push on it, and then you have to release afterwards.
I want to congratulate you for this extremely beautiful experiment. I'm very familiar with some of the technologies you use. The experiment is very carefully done, with systematic error, carefully checked. So just to summarize your thing, so obviously, as you have correctly said, other experiments should be done, and you looked yourself because of tremendous implication. So my first thing is to congratulate you. And it is very difficult for experimentalists to make comments about other people's experiments, because experiment has so many complicated things. Certainly, I am not qualified to comment on your things, but just the impression is it's an extremely well done experiment. So that is my number one. My number two is I was wondering if Professor Tekiki is here. Because in 1979, he was the person who proposed Gran Sasso, oriented Gran Sasso Hall towards CERN, and foresee one day this type of experiment should be done. And that I also want to congratulate him. I'll finish my comment.
Thanks a lot. I think we all share
Thank
somehow
you very
your
much.
congratulations. So first question about position. So Jasper, maybe, okay, so.
Let's assume that you really do have very, very good geodesy on the antenna. Okay, that I think has been demonstrated many times by the GPS. Now it's the transfer down underground that you've got. Now you have very, very impressive cross-checks on the timing. That looks very, very solid. But if I understand correctly, your cross-checks on the geodesy are basically to have had a team do it twice or something like that and come up with the same number. Now, if you do it twice, you might make the same systematic error twice. I mean, is there a completely independent way, drilling a hole down to the apparatus or, doing something totally crazy? Well, look, if this is a true measurement, drill a bloody hole, what's a hole? This is, we're trying to understand something very, very fundamental here. But you need a completely independent method rather than just repeating the same technique.
So I agree with you. In fact, if you want, there are two elements of cross-checks in this measurement. The fact that the measurements were taken at the two sides of the tunnel independently, and then when they crossed, they were within a few centimeters. This is the first cross-check. Second cross-check is that all this was already done at the time CNGS was started. And at the end, this new result is within 60 centimeters in agreement with the previous one. So it's within the error of the previous one. It's more precise because we wanted to achieve an accuracy better than 1 meter. So this was done. But it is also in agreement to the previous one within 60 centimeters. Then for what concerns the hole, we have been thinking about that. And for as far as we know, drilling a hole like you suggest can be done with 5% accuracy on its verticality. So if you do it over 1 kilometer, this will be a large uncertainty, much larger than what I've been quoting before.
Other question on geodesy with Tiziano?
It's again a little bit trying to understand whether there is any systematics which might be relevant. I'm here.
Here.
Now, in your paper, you claim that tidal deformations are negligible. And I can possibly assume that this is no other explanation, so I take it that you probably assume that given that you took data for a continuous period of time, any tidal deformation would average out.
Yes.
Now, but that does not apply to the fact that you took the geodesic measurement at a given time, which might have been affected, might have been with tidal deformations which were different from the average of 0, which is what... And I remember from the campaign we had here at CERN, in fact, I think here there's the intelligentsia about tidal deformation is concentrated at CERN. It was a few ppm effect in terms of the size of LEP, for example. So while it is, okay, still much below the 25 ppm effect which you seem to be measuring, I would not consider it negligible necessarily, and probably one should try to make an effort to see whether, because I've not seen anything to that extent. Can you comment on it?
Oh, okay, yes. Actually, I should give some more details on how these measurements were taken. In fact, they are not measurements which are concentrated in the time, but a campaign like that, it lasts at least 1 week of measurements. So you can cross-check the measurements outside the tunnel during 1 week. And this was done twice, as I mentioned. It was done in 2010, and then it was repeated in June 2011, so in completely different conditions. And the two measurements were in agreement at the centimeter level, as the geodesy people were expecting. So this is the kind of answer I can give you.
Walter?
Well, I think it's worth monitoring this distance as a function of the position of the moon, because the crust of the Earth is deformed by the moon and could have an effect of the order 10 to the -5. It's not a big effect, but I'm surprised that with two geodesic measurements you assume that to be a correct distance. I think it should be monitored according to the location of the moon.
Okay, indeed we took 3, taking also the previously existing one. And then you can see on this kind of plot that I'm showing, this is made on a very long time, and you don't see this kind of effects. These are high frequency data on the GPS. There are points which are computed at the minute level, and then in this plot there are points which are at the fraction of the day. And these kind of effects are not really visible by the measurements that we have been taking.
I have a comment on this. I'm sorry. Yeah. This is a local measurement. It is not something which is made of the baseline of 730 kilometers. Here you see just the position of the antenna, and you see that it doesn't move.
No, you are completely right. You are completely right, but it should be, however, affected by these movements, at least locally.
I can relay, because something I have to tell you, we are also in contact with the outside world in a way. I mean, some journalists are sending questions to Arnaud. And one question which comes from outside...
excuse me, the other point is that we take the data over, we took data over 3 years. So all this should average out, because these tidal movements are cyclic.
One question from outside is this kind of measurement, this kind of accuracy of 20 centimeter over 1,000 kilometer, is it something which has been done elsewhere? I mean, is it state of the art or far from the state of the art?
It's common, if you want, it's common practice. And the 20 centimeters are even a kind of bad performance, not related to the external points, which are at a centimeter level, but to the fact that we had to bring underground these measurements, and this was done in difficult conditions, because we had to do it in the highway, and we couldn't stop the traffic for 1 week in the highway. So at the end we negotiated to stop one lane, which is what you see there, one lane in one of the 2 tunnels. You know that there are 2 independent tunnels. So the traffic was stopped for 1 week, and then you had to work the triangulations in this small space corresponding to 1 lane. And so this justifies the 20 centimeters inaccuracy, but it can be done much better if we stop completely the traffic.
Maybe it's worth doing. Other question on the distance or yes, please.
Six years ago, I prepared a paper that explains that velocity greater than speed of light is possible in special relativity. And this paper is in your mail. Please look.
I said we can discuss it afterwards. I mean, maybe you just entered into the auditorium. Okay. Other question? No, I mean, is it about or timing now? Distance or timing? Please, John.
So it's actually a question about distance. So did you take into account the rotation of the Earth?
Yes, we performed the calculation, and it's a sub-nanosecond level effect.
Because if I'm not mistaken, Gran Sasso laboratory moves slightly further away from CERN during the rotation.
Yes.
Yeah, I also got the same estimate.
Yeah.
Okay. Gigi, sorry, Gigi.
You measure your waveform with all the protons.
Yes.
But then you detect only the central core of the beam. Has this any effect? I mean, is there any correlation? I have no idea.
Okay, so no, you ask a right question. So this is also related to the quality of the beam, of the CNGS beam, because as you say, as you point out, there might be, I don't know, some halos, some strange effects at the beam level. So, in the construction of the CNGS beam, for reasons of integrity of the target, because the target is subject to very big thermal shocks when it receives the protons, it was required to steer the proton beam within 500 microns from the center, the theoretical impact point at the center of the target. Actually, this is done much, much better, a factor 10 better. And the RMS, this is shown in this picture, is going from 50 to 90 microns if you consider the horizontal or the vertical dimension. And this has also been checked for what concerns the position of the muon centroid in the muon chambers, which reflects what happens at the level of the target. So the beam is also, the transfer line is essentially lossless. So what we measure in the BCT goes really in neutrinos. So by all these elements, we think that there is really no correlation between what happens at the level of the BCT and finally space correlations with the beam in Gran Sasso. This is just given by the kinematics of the pion decay, by this PT of the pion decay.
You know?
Just to clarify some statements in this seminar. Out of the two variables, distance and time, one is probably dominant in terms of error. My impression is that time is dominant.
Yeah, correct.
And another thing is that, a quick estimate in my head is show that of the order of 50, you need additional delay, for example, in the CERN side of the order of 50 nanoseconds to get the result. Is it correct or not?
Yes, we have many delays, but not just
No, I mean unaccounted delay of order.
Unaccounted delay.
Yes,
Yes.
50, 60 nanoseconds.
Yes, unaccounted
Or
delay.
at the level of what is the total delay which you have now?
What is the accuracy on the delay measurement?
No. What is the total delay?
The total delay is 60, the total delay at CERN.
Yes.
Well, these are large delays in some cases. I will show you the previous picture. Okay, so this is the setup at CERN. So for instance, here you have something like 10 microseconds. So this is what I showed is measured continuously since July.
The increase of systematic error, which would explain.
Yes.
So it seems to me that first statement is that time is dominant. And second, for example, if I look at where the time is coming from, the delay at CERN should be increased by about 15 nanoseconds.
That's correct.
Which is actually a small number compared to the total delay.
That's correct.
Augusto?
Yeah, Dario, thank you. I'm here, yes. So basically, when you do a time of flight, you have an arrival time and a departure time. And I believe you're making a very good job on the arrival time, but the departure time, as far as I understand, has a 10 microsecond uncertainty. Now, with 10,000 events or so, the overall uncertainty is 10 microseconds divided by square root of 10,000.
Indeed. As you mentioned, if you take just the uncertainty on the average time of this distribution, it may match what you were quoting. But we are performing this likelihood maximization, which takes into account all the delays, all the details of this distribution, and in particular the fronts, which play a big role in the determination of the statistical uncertainty. So this we have been checking also with the Monte Carlo techniques, because we can take this curve, which has been measured at CERN, and we can generate 100 opera experiments, for instance, with the typical statistics that we have been using for this measurement, and we can check the statistical accuracy on the results of these individual simulated experiments. So the fact that you perform this likelihood maximization by using all the features of this proton waveform allows you to bring the statistical uncertainty at this level of about 7 nanoseconds.
Jürgen, yes. Find the microphone.
This is a question concerning both space and time. Now, if one uses photomultipliers and scintillators, early arrival times can actually happen if a particle doesn't hit the scintillator but hits directly the photomultiplier and makes some Cherenkov flight, for example. Now, it so happens that your average delay time is just 60 nanoseconds. So did you check whether it's possible that some spray particles, instead of going into the scintillator, hit the photomultiplier, in particular as you always take the first one?
Yeah, so for what concerns the photomultiplier, you should take into account that we are in a really very quiet environment. So we have been checking also these rates by taking measurements when the photomultiplier is disconnected from the fibers. We have been measuring the dark count of the photomultipliers underground and so on. So this is a quiet environment. Then for what concerns the earliest heat, we also performed some cross-checks because, as I mentioned, we go through this Monte Carlo simulation, to which we attributed an uncertainty of 3 nanoseconds, a systematic uncertainty of 3 nanoseconds. And yes, this one. So we have been checking, for instance, by comparing the on track with respect to this earliest hit. We found differences at the nanosecond level which are comparable with the uncertainty that we are assuming on the simulation. Or we have been checking also the average time of the event without performing track reconstruction with respect to the earliest hit.
Tiziano, you had another question?
I'm trying to be diligent, so now I have a question on timing. Now, concerning this correction, I mean, I think you pointed out that the beam current transformer.
Yes.
You, besides checking it out with the pulsar, which is basically the cesium source, you wanted to see what was the response to proton. I think that was a very good idea. In fact, we have lived through difficulties for estimating the luminosity at LHC coming from the current transformer. Now, the point is that what you check there is really, I think, a different situation from what is the protons which you use. because you said you use an LHC injection cycle, so that is 50 nanosecond spacing of bunches which are a factor 10 at least intensity compared to the one you use, which are instead 5 nanoseconds separated and much lower intensity. Now again, I mean, I agree with you that you are measuring essentially the length of a cable. On the other end, it's obvious that I'm not sure that that you are using a representative proton bunch going through it and structure. So can you comment on that?
Yes. No,
it's
a good question.
Again, on the thing, I have another question. I mean, you showed in your analysis the effects of having 0 nanosecond difference, or 1048, which was the wrong, if you like, before opening the box calibration. I wonder how the chi-square would change from your fit if you moved it by
I will show you something. You're right.
Even that you're depending basically on
for what concerns the BCT, I didn't give all the details. So we performed also this calibration by injecting a signal from the cesium clock to the test input. So the test input is just another winding around the toroidal transformer which detects the beam. So this result is in agreement with the result of which we got with the beam, with the LHC beam. And then we took also measurements with the CNGS beam. And with the CNGS beam we have also a comparable result, but we have larger uncertainty. And the larger uncertainty is due to the fact that with the CNGS beam you have a continuous beam, and then it's difficult to make this kind of overlay that you see here, which here is unambiguous, because you have this comb that you have to overlay. In the case of the CNGS beam, you have an ambiguity of a couple of batches, which brings the systematic uncertainty to 10 nanoseconds, but the measurement was comparable. So at the end, we decided to use this measurement with the LHC beam, which is very clean, where there are no ambiguities in deciding who is who. Then for what concerns the other question that you raised, the one related to the change, because here you are right, it's difficult to see how the distribution will compare if you assume no effect. So there are some distributions that I can show you where you can compare the no effect, so the top computed assuming the speed of light, to the one. Okay, so here these are the distribution of the fronts. That's just part of the information. It doesn't depend just on that. So here you see what happens if you have no effect. So you have a systematic displacement of the red curve with respect to the experimental points. And this is by taking the effect coming from the likelihood maximization, which is 60.7 nanoseconds. So you see this kind of systematical displacement. And then this is for the first extraction. Then mentally you have to combine to the same information from the second extraction, which is shown here. And also here you see the same picture. There is a systematical anticipation of the points with respect to the curve, which is then fixed when you take the outcome of the likelihood. So this is just to give you an idea of the kind of effect that you could imagine to see on the fronts.
Just a question, sorry. John first, you will come later. Okay. Yeah, John.
So looking at the Minos paper from a few years ago, it seems that the dominant timing uncertainties are not associated with GPS and all that stuff, but actually internal to the detector. And in particular, the largest individual error seems to be associated with the antenna fiber length. And they make the comment that they measured this in several different ways and they got different answers.
Correct.
So my question to you, I guess, is how were you able to control this uncertainty a factor of 10 better than what they were?
That's correct. It's a very good question. I'm happy you asked it. So first of all, for what concerns the antenna, they didn't go through a calibration procedure from a metrology institute, apparently. Our receivers were calibrated with the antenna cable, as well. And you have seen the kind of agreement that then we got when PTB made this independent measurement. This exactly relies on this kind of calibrations like the antenna delay, the internal delay of the detector and so on. So there are means of calibrating this very precisely. I don't know why they didn't do that, but it can be done even rather quickly, this kind of operation. For what concerns the fibers, as I mentioned before, we don't measure the fibers by themselves, because then you go in this kind of situations where you use a technique which maybe is related to a different wavelength, to different equipment and so on. So we try to perform an inclusive measurement where we were measuring the delay which comes out from the two equipments before and after the transmission of the fibers, but we didn't measure the fiber individually. This is an inclusive measurement between two reference points of the timing chain, and this we repeated 2 times with the cesium, and even by making this 2-path measurement with another fiber, and they agreed at the nanosecond level. Maybe my timing friends would like to comment also on this.
I think your explanation was perfect and everybody understood it. I just wanted to say that I thank you for your kind words, and for the timing team at CERN. It was an incredible experience to work with you and with Julia.
Thank you. You want to
just a curiosity. There is some time dependence of this result. I mean, did you try to compare the results analyzing just the 2009 data set and the expression? Yes.
Maybe I was too fast, so that...
there is
so I will show it again.
Yeah, I think they were shown 2009, 10, and 11 are perfectly compatible.
Sorry if it was too fast. So this comparison is made at the blind level. So you see you have comparisons which concern data taken at the different periods of time in 2009, 2010, 2011. And then we made also a comparison. We made 2 bins, one for the data taken during the night and one during the day. And there is no difference within the system, the statistical uncertainty, and the same spring plus fall versus summer.
Okay, David?
Yes, first a general comment. You're not measuring any vectorial quantity here, so the title of the paper should be neutrino speed, not velocity. So that's the first comment. Now, the main issue here, I think, is you have a time of flight measurement, and you only have 2 measurements for the numerator, the geodesy. Can you go back to slide 32, please? Because you keep claiming that you measure things over 3 years, but your distance is measured only twice. And the 2 measurements here, I want to understand how the GPS, the X, Y, Z, T coordinates, they are different in the 3rd significant figure, but you claim uncertainties in the 7th significant figure. So I want to understand what that. So here, you see, yeah, this one here.
I skipped that, sorry. Yes, all right. Here, this one.
Yes.
Well, I don't know. I see here differences in the 3rd significant figure, I mean, in the different GPS, and but the end things combine down to uncertainties in the 7th significant figure. So I want to understand.
So, but these are not the same point. These are 4 different points. It's not the same point measured 4 times. Maybe I was not clear on that. I mentioned that we installed 2 benchmarks at the 2 sides of the tunnel. Benchmark means a reference point. So these are kind of monoliths that you measure. And the 1 and 2 are Teramo side, and 3 and 4 are L'Aquila side. And you get the coordinates of these 4 reference points, but you should not compare among themselves.
I think that the key thing here, because we are, I mean, it's a very important result. If it holds true, I think it's to really remeasure this distance. I think.
Yeah.
What about general relativity effects? Are those taken into account in this? Are those corrections important?
So that was a question from outside about that.
We took into account the general relativity effects at the level of the clocks, because the clocks in Gran Sasso and at CERN, they are not at the same height. But you have to take into account that these 2 clocks are not free running. They are continuously resynchronized through the common view mode. So this effect is at the level of 10 to the minus 13.
Just a moment, there was a question. Yes.
Your likelihood analysis gives information on a constant delay. What happens if the delay is not constant for some reason?
Yeah. Okay, so this is also a good question because it's really model related in the sense that when you try to analyze this data with respect to a particular theoretical model, you get some dispersion relationships, and you should have a shift, but also energy dependence, this kind of effects. So we deliberately decided not to go to this kind of procedure, but this is something that it could be done in the future.
Yes, please.
I want to ask a simple question. Is there a chance that due to some temperature variances between above the atmosphere and the Gran Sasso and there's a somewhat constant shift or varying shift between the GPS signals? Did you consider this? Okay, no.
Yes. For what concerns the GPS signals, the main corrections are at the level of the ionosphere. So it's not the local temperature. And these are taken into account with this P3 code, which is the combination of two different frequencies, which allow you to reconstruct the dispersion relations in the ionosphere. So then there are some residual systematic related to the P3 code. There is another kind of combination which is more precise, which allows you to perform measurements at the 100 picosecond level, but we were not interested in such accuracy. For us, 1 nanosecond was more than enough.
I have, okay, Maurizio, I think maybe we should try to finish.
Can you go back to the plot where we showed the difference between the no effect and the effect?
Yes.
Curves on top of your points. Do you agree that the effect is completely driven by the plots on the right? I mean, if I look at the plots on the left, I would say that two...
Well, there is also an effect. Okay, no, it's not this one. I have to go.
Which plot are you looking for?
Yeah, I know what he wants to see.
Yeah, it's one. Yeah.
Okay, this one. Okay. So, as I said, this is part of the picture, but you can see that there is also an effect of, it's difficult to judge by eyes, because then you have to take into account also the fluctuations of the points, but you see that there is a systematic effect also on this side. And then you have to combine with the other extraction, which is shown in the other page, where you can also see that there is a systematic shift.
If I look at the one on the bottom, it has the same fluctuation on the other side.
No, the fluctuations are there because...
no, but there is a directional fluctuation for the top P figure to prefer to go above the curve as much as I see in the center of your figure the same tendency of the points to be below your curve. So I would say that on the left, the fact that the 60.7 is preferred with respect to 0, it's a less evident statement, not at the 6 sigma level, of the fact that on the right, I see, I mean, on the right, I mean, if I do a binomial test on the plot on the top right, the one on the top is completely crazy. So what I'm wondering is, are we sure that the red curve that you measure here, it's not deformed by the fact that you're measuring the neutrinos up to 730 kilometers is by itself a selection rule that is biasing the shape?
Well, there are very...
which kind of systematics do you assign to the red
selection
shape?
rule on neutrinos arriving to Gran Sasso, this is what you mean?
I mean, what I'm saying is that are we sure that what you're getting in is an unbiased sample of the protons that are starting at CERN, or maybe you're getting a shorter view of the beam profile?
Yeah. So this goes to the comment I answered before, in the sense that as far as we know for what concerns the beam stability, the way the beam works, what we see in the BCT is entirely converted in neutrinos, and there is not such a dependence for what concerns the space position of the neutrinos which are detected by OPERA. I don't know if somebody from CNGS, Elias, do you want to add something?
Yes.
Maybe, Dario, you should stress that the fit is done globally.
Yes.
So all the peaks
Sure.
and valleys that you have in the center part play a role in the overall fit. So this is just an expansion, a zoom of the tails. Don't forget that there is a wide section of peaks and valleys.
The measurement, I guess, is completely dominated by the turn on and the turn off, because if I look at the curve on the plateau, I can fit everything on that.
Yes, I think the age are
No, there is also a role of what is happening in the middle.
Okay. I have also a question on this point. If you go to the previous one where you see the overall thing, I wonder... No, the one in
Yes, yes, I'm going there.
Okay.
Just a second.
My question is, what are the parameters? You also have a normalization parameter, not only because, you must have also a normalization parameter that you can play together with the shift. And looking to the other picture, it seemed to me that if you would allow a different normalization, you would, even the delta t equals 0 would not be so bad. In other words, how many, you have two things to worry. One is the delay, moving, but you also have a normalization, and the two things could be played together.
So, for what concerns the normalization, we are normalizing the curves on the number of events. So every waveform, a proton waveform, is normalized to the event which has been observed. If you take the area of these two curves, of the data and the proton curve, they correspond to the same number of events. So the normalization is fixed in this procedure. It's not free.
But not when you compare with the protons.
Yes, with the protons. Normalized to the number of neutrino interactions that we record in Gran Sasso. But not normalized through the cross-section. Normalized in the way that the two distributions correspond to the same number of events.
You had a comment? Yes.
So just to reformulate the comment by Maurizio, you are sampling only the core of the neutrino beam, which is quite broad at the Gran Sasso. So can it be that this time distribution is shortened because you are sampling the particles which, come most directly, because this is what he was asking for. This plot is showing 1 microsecond shift, but the other ones are showing the difference between 0 and 60 nanoseconds over 10 microseconds. So if you get a shorter burst, because you are sampling the core of the beam, then what he was saying is that you are just sensitive to the ending, so the turn off of the distribution, and this could make a shift which is not really a shift, it should be a shrink of the distribution. So this is the suggestion.
Yes. What do you mean by, which kind of relationship do you see between the core of the beam and the timing? That's the main question.
I'm not saying that this is the reason. I'm saying that he was asking whether you kept the
the stretching of the distribution as a free parameter.
Yeah, no, we didn't keep the stretching as a free parameter because this is also related to the possible dispersion and energy dependency. So, but then for what concerns your hypothetical relationship between the core and the timing, if you want the distribution of neutrinos in Gran Sasso is just broad because of the pion, the PT in the pion decay, is not really related to the timing issue of what you measure in the BCT. So this kind of relation is accidental. There is no correlation between the position in Gran Sasso and the timing that we measure at CERN. It would be very hard to explain this kind of relation.
But I don't know, for example, if the horn will become weak at the end of the beam speed,
okay,
for example.
That's a good question as well.
You have muon detectors which should be able to tell you whether the distribution at the beginning of the spill or at the end of the spill is the same, right?
Yeah.
Yes.
At least in the picture or in your paper there is muon detectors which...
So for what concerns, may I answer him first? So for what concerns the horn, the excitation of the horns lasts over several milliseconds. So we are just sampling a small part of it. I think that this plot is not even corresponding to the reality. It should have been zoomed on the flat part of the horns. Yeah.
Okay. There are so many questions, but we should... well, there was one over there first, but can you shout or use the microphone, please? And then
so this is a question purely about analysis, which is what you said was the third group.
Yeah, yes, we are already.
Fine. Hi, Dario. You mentioned that for the internal events, you make a division into two energy bins to check for effects. But for the external events, there is a correlation between the energy of the incoming muon and the distance travelled by the neutrino from the beamline, because the different because muons, neutrino to muon interactions taking place in different parts of the rock see a different amount of DEDX. So, do you want to comment on that?
Yeah, no, I understand what you mean. You don't know really where these muons have been generated, but I also showed you that if we remove completely these external muons, we get a result which is completely compatible within the systematics. This was one of the cross-checks that were shown.
Right, but it's... you could look for the same effect using something that only did, I'm asking you to comment really, because you could look for the same effect using something that only did muon.
For question, then we stop, I think, because there was
go
no
back
end.
to the...
Okay, so Bob first.
Could we go back to the edge plot again? I hate to ask a typecast question, but so if I remember correctly from Edie et al. And Fred James's book, if we idealize to a rectangular distribution, the maximum likelihood estimate of the location of the distribution just depends on the two extreme points, the average of the two extreme points or something like that. And so, in fact, it's hard for me to believe that your precision is coming from the... It's hard for me to believe that your precision is coming from the wiggles in the middle of the distribution. So I think we're close to the idealized case where it's the edges that's giving you your precision. And therefore the chi-square per degree of freedom, which is about 1, using the whole distribution does not really indicate how good the fit is, where you're fitting. So if you just chop off the whole flattish part of the distribution and fit to those two tails, I think one will get a much better sense of how good the fit is, and the lower right curve doesn't look, has a few points that are off. Let's put it that way. But quantifying that, I think.
Okay. Yes, we didn't put the numbers on the slides.
Pardon?
We didn't put these numbers on the slides, but you're right. One could quantify it in terms of chi-square in these regions, but I do not remember the number by heart. I don't have them on the slide.
Okay, just part. Okay, one more here. Okay.
You haven't said much about supernova data.
except that it's in the paper you mentioned that this is at 10 MeV, whereas you operate at 20 GeV. But you showed in your systematic checks that there was no energy dependence in your data, but you sort of say that you reconcile with the supernova exclusion at 10 to the minus 9 by saying, yeah, but that was at 10 MeV. Is there a chance you can reproduce the experiment at a different energy, for example, or how do you cope with that?
So how do we cope with that? This is a question related to the physics interpretation.
Yeah, I think that we are entering into interpretation. I mean, yes, you have seen they don't have the lever arm to do the energy dependence. They just show you that there is no obvious energy dependence, but that's all. I mean,
no, not cope philosophically, but you know, you say that you show your
show that we cannot claim an energy dependence within the accuracy of our measurement.
Okay. But by the way, then I think if we want to look at energy dependence, we should also look at this old Fermilab data, because they were going up. Although their accuracy was worse, they were going up to 200 GeV. So one should put all the points together. Last word to Gigi, and then maybe the last word Antonio would like to say a few words.
Discuss all these correlation things that we were discussing with many questions. Would it be possible to take data in the future with very much bunched protons, so that you get them every 5 nanoseconds to answer to all these questions?
Yeah.
And also in that case, you could really show that you can communicate to Gran Sasso faster than the speed of light, that you cannot do yet.
Yeah, no, that's a good suggestion. In the future, we may think to play with the time structure of the beam. This is something that, for instance, the people in the US will do for the next measurement, for sure.
I have another suggestion, which before I give to Antonio. Could one not bring a piece, just one scintillator of the opera detector or something like that, and with the same electronics, put it at the end of the neutrino beam, use different GPS, so as if it was completely independent experiments, and then you should find zero, because I think you are really at 1 kilometer or less than a kilometer. Right. Would it be possible, I mean, a cross-check of doing a near experiment where you should find zero? I mean,
it's a possibility to be investigated, yes.
Okay. So, Antonio, I think the last one.
No, first of all, I would like to say, following what Gigi just said, that we are planning to continue the studies. Okay, this was a side analysis for us. Now it's becoming one of the main issues. We should not forget that we still have to find some tau events, and for this,
we would like to see that.
And any discussion on the structure of the beam should not compromise the intensity. So this is clear. On the other hand, I would say that on behalf of the collaboration, we are very grateful to all of you for all the stimulating questions of which we took note carefully, and we stored all the nasty questions and suggestions. So thank you very much. And I would recommend you, just for those of you who not the opportunity to ask a question, to send me an email to me and saying that I was attending the meeting, I want to ask this question. Just to separate from the spam of science fiction. Okay, so thank you very much on behalf of Open.
Okay, I think we should all really thank, first of all, congratulate the Opera collaboration, and thank Dario. I mean, he did a fantastic job. Merci, please. C'est bien, tu t'es bien.